Hi everybody, welcome back to term 4, last term. Hopefully you've had a good break. I certainly have, but it's time to get back into some methods, so have a look at your handout. 19b, the derived function, and what we're doing is we're going to differentiate. Now, the derivative function is also known as the gradient function, and really what it means is when you find the diff, you can find the gradient on the curve at a particular x-coordinate. First of all, let's look at these three rules. First of all, we've got what's called the power rule. Now, if we have a function, f of x, which is just x to the power of n, then if we diff it, we write it as f dash of x. What happens is our power comes to the front. We have our rule, but we decrease the power by 1. This is called the power rule. We can use this a lot. Further to the power rule, let's say if there's a constant in front of it, we're going to do the same thing. So if we diff it to find f dash of x, again the power comes to the front and we decrease the power by 1. So as you can see, it's the same as what we had before, except that we now multiply by the constant. Here we have a function f of x which is made up of two functions, g of x and h of x. If we want to find the diff of f of x, in fact we can just find the diff of g of x and the diff of h of x. So we can write this as the diff of g of x and the diff of h of x. And we will use this property of differentiation a lot. Last rule here is called the product rule, which says that if we have a function f of x which is made up by two functions multiplied together, then the diff is g of x multiplied by the diff of h of x, so h dash of x, plus the second function h of x times the diff of the first function. This is called the product rule. So here's a few types of differentiation rules. Now, this first example says use first principles to differentiate this function. Now, these are all shortcuts. This first example, though, is revision from what we did last term, where we said if we want to find the derivative using first principles, this is equal to the limit as h approaches 0 of f of x plus h, take f of x all divided by h. Nope, can't find my ruler. Okay, this is not going to be nice. Now, to sub into here, instead of f of x, I have f of x plus h. So wherever I see x here and here, I replace with x plus h. So I'm going to rewrite this as it's the limit as h approaches 0 of, instead of x, I have x plus h. So it's going to be 4 times x plus h all squared. Replace this x with x plus h. Take away f of x, which is this, all over h. As you can see, I was very careful with my brackets. Anytime I replace the x with x plus h, I put it in brackets. Here, when I do take f of x, I subtract this whole function in brackets. So I'm going to expand here. So it's the limit as h approaches 0. This is going to be 4x squared plus 8 hx plus 4h squared. Take 5x, take 5h, take 4x squared plus 5x all over h. And so of course what we're going to do is collect like terms here. So my 4x squareds are going to go away. This 5x and this 5x we're going to cancel. So here's what I'm left with. 8hx plus 4h squared take 5h. Now obviously we can't divide by 0 here, so we'll take out h as a factor on top. So there's a limit as h approaches 0, take out the h. We've got 8x plus 4h, take 5, all over h. H's will cancel, and so as h approaches 0, we can say that the derivative is 8x take 5. Let's now use our new rules that we've established at the beginning here for the remainder of these questions. So let's have a look here. Find the derivative of y equals x cubed. Now for the derivative we're going to write it as dy and dx. As we know, what we're going to do is the power will come to the front. So we have 3x, and then decrease the power by 1. Over here, for part B, same thing, dy on dx, and we're just going to diff each individual term. So when we diff the first one, the 3 comes to the front, multiplies by the 4, gives us 12. Then we decrease the power. Now this is 3x to the power of 1. What will happen is the 1 will come to the front, we have negative 3, and it'll become x to the power of 0. Now anything to the power of 0 is 1, so what we'll be left with is negative 3. And in fact, anytime you see just an x term, the coefficient is going to be the diff. And now for plus 2, this is actually 2x to the power of 0, and when we have the 0 times by the 2, that becomes 0. So in fact, any constant when we diff it will go away. And so when we diff it, we get 12x squared take 3. If we look over here then, we can see immediately that because it's just an x term, when we diff it, we just get 10. Over here, this is just a constant. So when we diff it, we're left with nothing, we're left with 0. This example here, we can use the product rule. So it's going to be 2x plus 1 times the diff of x plus 2 plus x plus 2 times the diff of 2x plus 1. So it's 2x plus 1 multiplied by the diff of x plus 2. Now the diff of x plus 2 is just 1. Plus x plus 2 times the diff of 2x plus 1. The diff of 2x plus 1 is 2. So I'll just collect like terms here. So this is going to be 4x plus 5. Now you might say, could I have expanded this first and then just diffed it? Absolutely, you can do that. But if there's a chance to use the product rule, I will use the product rule. Example 3, find the gradient of this curve when x equals negative 2. Now to do that, what we're going to do is we're going to diff it. And when we diff it, we get the gradient function. If we sub in negative 2 into the gradient function, it will tell us the gradient of the tangent at that point when x equals negative 2. So let's go ahead and diff it. Now this 3 will multiply by the negative 2, so we get negative 6x. We decrease the power. For the second term, we have 3 times 2. We decrease the power, so 2 becomes 1. So this is the diff. Now when x equals negative 2, all we have to do is we have to just sub in negative 2. Just be careful here with all the brackets. Whenever I'm replacing x, I'll use brackets. Like so. So that when I expand here, I'm going to be careful. So this is, this becomes negative 2 times negative 2, which is positive 4, times negative 6. This is negative 24. Take 12, so this is negative 36. Now, what is this really doing? I mean, let's say if I graph this curve, right? So let's say if I just took out a common factor of negative x squared, I'd be left with 2x take 3, because that's negative 2x cubed plus 3x squared. Let's say if I did that, if I sketch this, okay, my intercept is the origin, 0, 0, and 1.5. Now this is an inverted cubic, so it would look something like this. And what it's saying is that when x equals negative 2, let's say over here, what's the gradient of this tangent? Now it's going to be really negative. In fact, it's going to be negative 36. It's going to be much more negative than I'm even shown there. That's just a quick idea to see what this question is really saying. Last one, find the coordinates of the point on this curve when the gradient is 0. So let's diff it and find the gradient function. And then when is the gradient 0? So to find the diff, it's going to be 2x take 4. This is the gradient function. The question is, when's the gradient 0? So if I solve for x here, I get x equals 2. However, find the coordinates. So I need to sub back in. So when x equals 2, y is 2 squared take 4 times 2 plus 2. Y is negative 2. So therefore, as coordinates, it's going to be 2, negative 2. Now again, you might say, what does this mean? This means that, let's say if we sketch this, and what I'll do is I'll complete the square. So this is x take 2 or squared take 2. If I was to sketch this, there's a turning point at 2, negative 2. So it would be a parabola, something like this, and the tangent here has a gradient of 0. And so this question is saying find the coordinates of the point on the curve where the gradient is 0. Here it is. At the turning point, 2, negative 2. But we found the gradient function, set it equal to 0, sub back into the original to get the coordinates. So if you can, please spend the rest of this period working on the 19B questions. I'll be back tomorrow and we'll be looking at 19C.